Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back. Today, we are strapping ourselves into the cosmic equivalent of a particle detector, I guess you could say, and heading straight for the abyss. Okay, let's unpack this. We're diving headfirst into, well, the biggest mystery out there, really. Dark matter, that invisible stuff making up, 85% of the universe's matter. And the sources we're digging into today, mainly this really fascinating study in physical review letters, they suggest something pretty astonishing, that the most extreme places, supermassive black holes, might actually be the best place to find it. The really surprising twist, though, is how. Those amazing images from the Event Horizon Telescope, the EHT, of M87 and our own Sagittarius A, turns out they're more than just, mind-bending pictures of spacetime. They're actually being used now through some incredibly sophisticated modeling as these ultra-sensitive detectors for dark matter. We're going to explore exactly why the darkest spot, the black hole shadow, is somehow the key.
Yeah, it's a genuinely innovative approach. It really required a different way of thinking. For decades, the hunt for dark matter has mostly been, either deep underground labs looking for direct hits or telescopes looking for signals across the galaxy, right? What's so powerful here, and kind of cool, is that this black hole imaging method connects three usually quite separate fields. Sure. You've got gravity, particle physics, and cutting-edge observation all rolled into one. Before we get into the black hole as a detector, maybe we should just quickly ground this whole dark matter thing for you, the listener. Why are we even so sure it's 85% if we've never seen a particle?
Well, it all comes down to gravity, really. We see things in the universe galaxy spinning way too fast, light bending around clusters more than it should, patterns in the early universe light. None of it adds up with just the normal matter we see. So there has to be this invisible scaffolding, this dark matter providing the extra gravity. Our mission today, then, is to connect those gravitational clues to these new black hole observations.
We'll explain why that dark spot is, counterintuitively maybe, our best shot at finding the invisible.
Okay, let's start with the tech itself then. The Event Horizon Telescope. When we see those, those famous orange rings, we're looking at something pretty revolutionary. We say it's a global network, but what does that actually mean in practice? It's not just one big dish.
Not at all. It's an array of telescopes scattered across the globe. Chile, Hawaii, Spain, Antarctica, you name it. They all stare at the same black hole simultaneously, and they synchronize everything using incredibly precise atomic clocks. The amount of data they record is just staggering, petabytes.
And that synchronization, that's the trick, right? That VLBI thing.
Exactly. Very long baseline interferometry. Think about trying to see something incredibly tiny far away, like spotting a donut on the moon. No single dish on Earth is physically big enough. But VLBI lets you combine the signals from all these separate telescopes. You feed all that data into supercomputers, correlate it, and, you effectively create a virtual telescope as big as the Earth itself.
Wow.
That's how they get the insane resolution needed to see the glowing gas right at the edge of the event horizon.
That resolution is definitely key. So what are they actually seeing there? What's making that light?
Fundamentally, it's synchrotron radiation. You've got electrons heated up to billions of degrees, just insanely hot, spiraling around super intense magnetic field lines very close to the black hole. They emit this specific kind of light, and the EHT observes it at a wavelength of 1.3 millimeters, or 230 gigahertz. That frequency is special because it can actually punch through all the dense gas and dust surrounding the black hole, giving us a clearer view.
The scale of it all, the extremes. It's just mind-boggling. I remember reading Jing Xu, one of the co-authors, mentioned being fascinated by how the EHT pushes right up against the boundaries of known physics.
Absolutely, and that's precisely why the theoretical models are so crucial. You can't just interpret that image by eye. To understand the shape, the brightness, and especially that central dark patch, the shadow astrophysicists rely totally on complex computer simulations. They simulate the plasma, how it moves, how it radiates. And the model that's been really successful, the one that best explains what we see for both M87 and Sagittarius A, is called the magnetically arrested disk model. Or MAD.
Okay, we probably need to spend a moment on this because you said it's foundational for the dark matter hunt. What exactly is a magnetically arrested disk? How is it different from, say, older ideas about how black holes feed?
Right. Well, older models, sometimes called Saini standard, and normal evolution pictured a sort of thick hot disk with maybe weaker, more tangled magnetic fields. The MAD model is fundamentally different. It describes a situation where the accretion disk, the inflowing gas, is threaded by incredibly strong, well-ordered magnetic fields, so strong, in fact, that they dominate the dynamics.
So the magnetism isn't just along for the ride, it's actually controlling the flow.
Precisely. These powerful fields essentially act like a dam or a bottleneck. They slow down or arrest the rate at which matter can actually fall into the black hole. And crucially, these strong organized fields are also thought to be the engine that launches those enormous jets we sometimes see shooting out from black holes perpendicular to the disk. Matching the observations, especially how relatively faint our own SGRA is, really points towards something like the MAD scenario being at play.
Okay, so strong magnetic fields controlling the flow. But the key question for this dark matter search, why does the MAD model explain the shadow? Why is it dark in the middle?
Ah, yes. It explains it very elegantly. In the MAD simulations, the vast majority of the light-emitting electrons, the ones producing that synchrotron radiation we see, are confined to that bright, turbulent, dense accretion disk rotating around the black hole's equator. But the regions directly above and below the disk, this kind of funnel area where the jets would launch from, those regions are magnetically dominated, but according to the simulations, they are relatively particle poor. There just aren't many electrons there to radiate light.
So the light source is mainly in the donut, not in the hole or above below it.
Exactly. That funnel of low-density plasma means there's much less light coming from that central region towards us. This sharp difference between the bright disk and the particle-poor funnel creates that stark contrast we see in the EHT images, the bright ring against the dark central void. It's like the black hole's own physics has created a cosmic darkroom for us.
Okay, that sets the baseline picture really clearly. We've got the black hole, extreme gravity, these super strong organized magnetic fields from the MAD model, and a dark shadow because the jets basically clear out the normal light-emitting stuff. Here's where it gets really interesting. Now we switch gears from the known astrophysics to the hypothetical particle physics. What happens when dark matter, which only really cares about gravity, meets this ultimate gravity trap?
Right. So as you said, dark matter mostly ignores everything except gravity. But the black hole's gravity is immense. It's the ultimate concentrator. Over billions of years, the supermassive black hole just sits there, and its gravitational pull relentlessly draws in dark matter particles from the surrounding halo. They get pulled inwards, pile up, and create this incredibly dense region right near the black hole. Physicists call this a dark matter spike.
The spike. How certain are we that these spikes should actually form? Does it depend much on what the dark matter distribution looked like way out in the galaxy to begin with?
That's a fair question. The exact profile of the spike does depend a bit on the initial conditions, the original dark matter halo shape, which has uncertainties. But the basic mechanism, the formation of a spike, is a pretty robust prediction. It happens through something called adiabatic contraction. As the central mass, the black hole, grows over cosmic time, its gravity pulls the surrounding dark matter inward, compressing it and boosting its density way, way up. This should happen for the standard kind of cold, non-interacting dark matter candidates most people consider.
And when you say boosted way up, what kind of densities are we talking about near the event horizon?
We're talking orders of magnitude higher than the background. Out here near the sun, the dark matter density is maybe 0.3 GeV per cubic centimeter, something like that. But right inside that spike near the event horizon, simulations suggest it could be 105.55, maybe even 166 times higher. It's a phenomenal concentration in a relatively small region.
Okay, 1,000,000 times denser. Why is that density boost so critical for trying to detect it compared to just looking elsewhere?
It boils down to how many proposed dark matter particles might actually signal their presence. For a large class of candidates, the WIMPs, weakly interacting massive particles, are the classic example. The idea is that when two dark matter particles collide, they can annihilate each other. And that annihilation produces standard model particles. We can detect things like electrons and their antimatter counterparts, positrons. These then radiate light, like synchrotron radiation, that we could potentially see.
Okay, so collisions produce light.
Yes, but here's the crucial part. The rate of those collisions, the number of annihilations happening per second, depends on the density squared.
That's true.
Yeah, because you need two particles to find each other in the same place to collide. So if you boost the density by a factor of 1,000,000...
The annihilation signal doesn't just go up by 1,000,000, it goes up by 1,000,000 times 1,000,000.
Yeah.
1,000,000,000,000 times stronger.
Exactly. That quadratic dependence is why this tiny region, the dark matter spike, becomes such an incredibly promising place to look, potentially much brighter in dark matter annihilation signals than anywhere else in the galaxy. And Yifan Ken, another co-author, put it really well. He said something like, ordinary astrophysical plasma is often expelled by powerful jets, leaving the shadow region especially faint, which we just discussed. Dark matter, however, could continuously inject new particles that radiate in this region.
That's really elegant. So the black hole's own powerful outflows, the MAD physics, conveniently cleans out the background noise, the normal light in that central shadow region. But gravity, which dark matter does feel, creates the spike, which then acts like a continuous source, constantly seeding that same dark region with new particles that can produce light if they annihilate. It's like nature set up the perfect contrast experiment for us.
Precisely. You're looking for a potentially faint signal against a naturally minimized background. It's an ideal testing ground.
Okay, the concept is brilliant dark matter spike meets dark shadow. But turning that idea into actual reliable science sounds incredibly difficult. How did the team actually model this? It wasn't just back of the envelope stuff, right?
Oh, definitely not. This required a really sophisticated framework. Previous attempts often used, let's say, oversimplified pictures, maybe assuming everything was perfectly spherical around the black hole. Easy to calculate, but not very realistic. This new work had to build the dark matter physics directly onto the complex, established astrophysical picture from the MAD model simulations.
So they had to combine the two worlds.
Exactly. They used these huge computer simulations called general relativistic magnetohydrodynamic simulations, GRMHD, and combine that with detailed modeling of how the dark matter annihilation products would actually propagate.
Whoa, okay, GRMHD, let's break that down. General relativistic magnetohydrodynamic. Why do you need all three pieces together? Sounds complicated.
It is, but you need all three because the environment is so extreme. General relativistic because gravity near the black hole is intense, space-time is warped, so Newtonian physics just won't cut it. Magneto because, as we established with the MAD model, the magnetic fields are super strong and basically dictate how the plasma moves and looks. And hydrodynamic because you're dealing with the flow of a fluid, the plasma, the super hot gas falling in. You really can't model that environment accurately without putting all three pieces, GRM and HD, together.
Right, so they run these massive GRMHD simulations, which gives them a realistic 3D map of the plasma, the magnetic fields, everything around M87 or SGRA. But then how do they layer the dark matter physics on top without it just getting lost in the noise or the uncertainties of the simulation itself?
That's the core challenge and where this framework really pushed things forward. They didn't just calculate a theoretical spike density and call it a day. They took the actual messy, asymmetric, time-varying magnetic field structure directly from the validated GRMHD simulations, the same fields shaping the light we already see. Then they simulated what would happen if you injected a new population of particles, the electrons and positrons, from hypothetical dark matter annihilation into that exact magnetic environment.
Ah, okay. So they tracked the journey of these hypothetical particles.
Exactly. They modeled the whole particle propagation. An electron or positron pops into existence from an annihilation, finds itself in this intense, complex magnetic field, starts spiraling, interacting, losing energy via synchrotron radiation. The simulation tracks all of that. It calculates precisely what the light signature from those specific particles born from dark matter would look like, given the realistic magnetic landscape they find themselves in. It's like forensic physics, tracing the path and radiation of these hypothetical byproducts.
It's tracing the potential evidence within the known crime scene, basically.
That's a good way to put it. And as Jingshu pointed out, the light we normally see from the EHT comes from the regular astrophysical electrons, and we think we understand their behavior pretty well from the MAD model. But if dark matter is annihilating, it produces these extra electrons and positrons. And crucially, their radiation might look subtly different, partly because they're being injected more broadly, even into those particle-poor jet regions, not just stuck in the disk.
And did they test different kinds of dark matter, different masses or ways it could annihilate?
Yes, absolutely. To cast a wide net, they looked at two main possibilities for what the dark matter could annihilate into. First, into pairs of bottom quarks and antiquarks, which is a common channel in many theories. Second, directly into electron-positron pairs. And they tested this across a huge range of possible dark matter particle masses from less than a GeV, so lighter than a proton, all the way up to about 10 TeV, which is incredibly heavy, like thousands of protons. So they covered a lot of the theoretical ground.
This brings us to what feels like the most critical and maybe the cleverest part of their method. They aren't just looking at how bright the black hole is overall. It's all about the shape, the spatial pattern of the light, the morphology.
Exactly. This is the real innovation that turns the EHT into such a potentially powerful dark matter probe. Let's just remind ourselves and the listener of the two different shapes we're comparing. First, the baseline, the normal astrophysical light predicted by the MAD model. That light is sharply concentrated around the equator, the bright, turbulent disk. The central funnel region, the shadow, is left very dark.
Right. Bright donut, dark hole. Now contrast that with the signal you'd expect from the dark matter spike.
Well, the dark matter spike's shape is dictated purely by gravity, not by the magnetic fields confining the plasma. So it's expected to be much more spherical, or at least more uniformly distributed around the black hole. Therefore, the electrons and positrons produced by dark matter annihilation would also be injected more uniformly, importantly, including inside that central funnel region, the part that's usually dark.
So the dark matter signal would effectively tend to fill in the shadow region a little bit, because dark matter keeps supplying particles there, even where the jets have swept out all the normal plasma.
Precisely. That subtle difference in shape, how dark the shadow actually is, compared to how dark the MAD model predicts it should be, that's the key insight. That's the aha moment. Instead of looking for some huge flare-up in overall brightness, which could be caused by lots of astrophysical things, they're looking for a specific morphological signature. Is the shadow slightly less dark, slightly more filled in, especially near the center than expected? If yes, that could be dark matter.
Okay, that makes sense. So how did they practically compare this idea to the actual EHT images?
What the researchers did was generate hundreds, maybe thousands, of synthetic EHT images. Each simulated image started with the baseline astrophysical emission from their best MAD model. Then they added on top of that the predicted signal from dark matter annihilation, trying out different strengths. What would it look like if dark matter annihilated very weakly, moderately, strongly? So they had a whole library of possibilities.
Like generating suspect profiles to compare against the evidence.
Exactly. They then took these synthetic images and carefully compared them, pixel by pixel almost, against the real EHT data for M87. They focused specifically on that crucial inner shadow region, the dark room, where the normal astrophysical light should be at its absolute minimum. They were hunting for any subtle excess brightness, any deviation from the expected deep darkness that matched the pattern predicted for a dark matter signal.
The power in that approach seems huge. It treats the black hole shadow as this incredibly sensitive null experiment. If the shadow looks exactly as dark as the MAD model predicts, with no extra light filling it in,
then that sets an upper limit on how strongly dark matter can be annihilating. It tells you the dark matter cross-section must be below a certain value, otherwise you would have seen that extra light.
And this morphological approach, looking at the shape, was much more powerful than just looking at the total light. Why is that inherently better?
Because the total brightness is really sensitive to all sorts of messy astrophysical details. We call them nuisance parameters, like maybe the black hole's accretion rate just happened to burp and get a bit brighter that day. That could easily mimic or completely swamp a faint, steady dark matter signal if you only looked at total intensity.
Right, the overall brightness can fluctuate a lot.
Exactly. But the shape, the morphology specifically, the contrast between the ring and the deep central shadow is much more robustly predicted by the fundamental MAD physics. Even if the whole thing gets a bit brighter, the normal astrophysical electrons should still be mostly confined to the disk region. The dark matter signal, however, would still be more spread out, still trying to fill in that shadow. By demanding that the dark matter signal doesn't exceed the observed brightness anywhere in the image, especially deep inside the shadow, they get a much tighter, more reliable constraint that's less affected by those overall brightness wobbles.
Okay, let's get concrete then, translating all this complex modeling into results. Using the current EHT data, mainly for M87, what did they actually manage to rule out? What part of the dark matter possibility space did they carve away?
They set some pretty significant limits, actually. The analysis managed to exclude quite large regions of parameter space for dark matter annihilation that hadn't been probed before by other methods. Specifically, looking at the current EHT images, they could set upper limits on the annihilation cross-section down to about 1027 centimeters.
Okay, 1027 centimeters. So that number needs some context for us and for the listener. What exactly is a cross-section, and why is getting down to 1027 a big deal?
Right. So the annihilation cross-section, often written as sigma VLR, is basically a measure of how likely two dark matter particles are to actually find each other and annihilate when they meet. Think of it like the effective target size for the interaction. Bigger cross-section means more annihilations, easier to detect. Now, for decades, there's been this benchmark target value in the WIMP paradigm called the thermal relic cross-section. It's roughly the interaction strength needed for dark matter to naturally end up with the abundance we observe today, having been produced in the hot early universe.
And what value is that benchmark?
The thermal relic value is generally taken to be around $3 times 1026 meters. So the limit they reach, 1027 centimeters, is about 30 times smaller than that key theoretical target.
Wow, okay, so smaller is better here. They're ruling out possibilities well below the classic benchmark.
Exactly. The smaller the cross-section limit you can set, the stronger your constraint is, because you're probing dark matter candidates that interact more weakly, that are more elusive. Reaching 1027 with current data is genuinely competitive and impressive.
And as Yifan Chen pointed out, these limits just from the existing EHT images are already better than some other searches that might rely on similar assumptions about the dark matter spike, mainly because the EHT gives you this clean look right at the point of highest density.
That's right. It's a very direct probe of that specific high-density region.
I have to push back a bit, though, play skeptic for a moment. You mentioned the May model is complex. Simulations have uncertainties. How sure can we be that these dark matter limits are really robust? What if, say, the black hole's spin is a bit different than assumed, or the plasma physics isn't perfectly captured? Couldn't that change the predicted shadow shape enough to mess up the dark matter constraints?
That's absolutely the critical question to ask, and it's something the researchers addressed very thoroughly. They ran extensive tests, deliberately varying those nuisance parameters you mentioned. They reran their analysis, assuming different values for the black hole spin, from non-spinning up to maximally spinning, and varying assumptions about the plasma, like the ratio of electron to proton temperatures, which is notoriously hard to pin down.
And what happened? Did the limits change wildly?
Remarkably, no. They found that the derived constraints on the dark matter annihilation cross-section remained robust against astrophysical uncertainties.
Why is that? Why aren't the limits more sensitive to those details?
It comes back to morphology being key. While changing the spin or plasma details does affect things like the exact size or the overall brightness of the ring, it has less impact on the fundamental shape characteristic of the MAMID model, namely that deep central depression, the shadow, caused by the particle pore funnel. Since the method is fundamentally looking for excess light filling in that shadow, a signature distinct from the main ring emission, the constraints hold up surprisingly well even when you tweak those other astrophysical parameters. This makes the results particularly compelling and trustworthy.
That robustness is really important. Okay, so if they can get such strong limits with current EHT data, despite its limitations, what happens when the EHT gets its planned upgrades? The potential must be huge.
Oh, the potential is truly transformative. The next generation EHT, the Ang EHT, involves adding more telescopes to the array, observing at additional frequencies, and generally upgrading the technology. One of the headline goals is to increase the telescope's dynamic range by nearly 100 times.
100 times dynamic range.
Yeah.
That sounds like a massive improvement. Can you help us visualize what that actually means for looking at a black hole?
Yeah, it's a bit abstract. Chen used a nice analogy. Think about the HDR or high dynamic range mode on your smartphone camera.
Okay, yeah. That lets you see details in both the bright sky and the dark shadows in the same photo.
Exactly. The current EHT is a bit like a non-HDR camera trying to photograph the incredibly bright accretion ring right next to the incredibly dark shadow. It struggles to capture detail in both simultaneously. The NEHT, with its 100x dynamic range boost, will be like turning on super HDR. It will allow scientists to reveal very faint details right next to extremely bright features. And that's precisely what the dark matter signal is expected to be, a faint glow inside the shadow right next to the blazing ring.
So much better contrast. What about resolution? Getting a sharper picture?
That too. The upgrades aim to improve the angular resolution down to the scale of about 1 gravitational radius. That's zooming in incredibly close, right to the mathematical edge of the black hole itself. This will allow them to probe even deeper into the very darkest parts of the shadow, where the astrophysical background light is predicted to be at its absolute minimum, making the contrast with any potential dark matter signal even sharper.
So higher dynamic range, better resolution. With that kind of power, how far could they push the search for dark matter annihilation? Could they reach that benchmark thermal relic value?
That's the exciting prospect. Simulations suggest that these future enhancements could potentially allow detection of or set limits on dark matter annihilating with a cross-section right around that key thermal relic value, the $3 times 1026 centimeters number. And they could potentially do this for dark matter particle masses all the way up to 10 TeV or even higher. So yes, the NEHT could realistically start probing and potentially ruling out or even detecting some of the most theoretically favored WIMP dark matter candidates.
That's a huge goal. And are there other new techniques they can use with the upgraded EHT beyond just looking at the brightness and shape in one image?
Yes, definitely. The researchers are looking beyond just intensity maps. The EHT is evolving into this multi-layered analysis platform. 2 big frontiers stand out.
Okay, what's the first?
The first is using polarization data. Light has polarization. It's basically the orientation of the light wave's electric field as it travels. The EHT can measure this polarization, not just the intensity. Why does that help? Because the polarization pattern is directly shaped by the magnetic field structure and the plasma dynamics near the black hole. It contains information that simple brightness maps don't. So by analyzing the polarization patterns, scientists can get a much more detailed check on whether the magnetic fields really do look like the May-D model predicts. This helps confirm their baseline astrophysical model is correct before they even start looking for the tiny dark matter deviations. It adds another layer of confidence.
Okay, polarization gives you magnetic field info. What's the second new frontier?
That would be multi-frequency observations. The idea here is to observe the black hole not just at the current 230 gigahertz, but at several different radio frequencies simultaneously.
How does looking in different colors help distinguish dark matter?
Because different ways of producing light often have different dependencies on frequency, they have different spectra. The standard synchrotron radiation from the hot plasma in the disk has a known spectral shape. Its brightness changes in a predictable way as you change frequency. Now, if dark matter annihilation is also producing electrons and positrons that radiate, their light might have a slightly different spectral shape. Maybe it falls off less steeply with frequency, or has some other characteristic signature, because the particles are being injected differently. So, by measuring the brightness and shape of the emission at multiple frequencies, researchers can try to separate the components based on their color. It's like having another knob to turn, another diagnostic tool to distinguish a potential dark matter signal from the complex astrophysical foreground. It provides a crucial cross-check.
This really does change the game. We started out thinking of black holes mostly as these cosmic vacuum cleaners just swallowing everything. But this work, blending the general relativity simulations with particle physics, it reframes them as these incredibly precise natural laboratories, acting as both particle accelerators maybe, and definitely as ultra-sensitive detectors. So what does this all mean for you as a listener? I think it means the hunt for dark matter has taken a really sophisticated turn. We've moved beyond just looking for bumps in brightness. Now it's about detailed morphological analysis, reading the shape of the light and shadow, using the black hole's own extreme gravity to amplify potential signals. It's a powerful new way to probe the nature of that invisible 85% of the universe.
It really is an amazing example of scientific creativity, isn't it? Using the most extreme gravitational environments we know of to search for potentially undiscovered fundamental particles. And it underscores a really important point. Even places that seem empty, like the shadow of a black hole, aren't really empty. They're dynamic regions filled with physics, potential laboratories just waiting for us to develop clever enough ways to read them. Which leads to maybe a final thought for you to ponder. If the black hole shadow isn't just a static silhouette, but this dynamic, multi-layered lab letting us probe particle physics by analyzing its shape and contrast, what other deep fundamental questions about the universe might we be able to answer by looking closely at the geometry of these seemingly empty spaces? What else might be hiding in the shadows?